Yeah, that was a photo finish coming in. How about that? Am I amplified?
Who said that?
How about now? Okay. All right. Yay, I'm here. Okay. We had about 36 hours of technical problems, all having to do with computers, and we all know how we love computers. So that left us running right to the last minute. But we're here, so that's all that matters. Yay! Okay.
You were all really close to having to interpret dance this show for us.
Yeah, that's right. So what's this? That's a supernova.
Yeah.
Okay. All right. The other thing you learn when you do a public speaking and you wear dresses without pockets, you have no place to put your mic pack. So, okay. Enough of these problems. I'm here. I'm grounded. I'm going to tell you all about all kinds of cool stuff. Welcome to All Space Considered. How many of you have been here before? Oh, I love that. How many of you have never been to All Space Considered before? I love that too. There's so many of you. That's my goodness. That's wonderful. So if you've never been here before, then you will be maybe surprised to learn that this show happens on the first Friday of every month. We're always here on Friday. These are various ways, on the first Friday of every month, these are the various ways that you can reach us. We, when I say us, are, I'm Dr. Laura Danley. I'm the curator of Griffith Observatory. And next to me is Dr. David Reitzel, the astronomical lecturer. And next to him is Patrick So, the theater programs manager. And we are your usual All Space Considered crew. Tony Cook, who is often here, always here in fact, is taking a little sabbatical from the show because he has so many things going on that he needed a little bit more time. So through the end of the year we will be without Tony Cook, but I know. Oh, hear that, Tony? Forget about those telescopes. Come back to All Space Considered. So we're very happy to have you here. How many of you are members of Friends of the Observatory? That is a really nice number. And imagine how happy you would be if you had your hand up too. So that would be a way of encouraging to consider becoming a member of Friends of the Observatory. Friends of the Observatory is our sister 501c3 support and membership organization. They do amazing things for us, like support our 5th grade school field trip program. So if you like 10-year-olds or you think they may be our future, he said that earlier too. Okay, even if you don't like 10-year-olds, but you recognize that they will be the decision makers of the future and need to love science, then you may want to consider supporting Friends of the Observatory that makes it possible for them to come to this field trip program. And so many other things that Friends of the Observatory does. Look at the website, learn all about it, and then become a member. The other people that we like to thank are the tax-paying citizens of Los Angeles. Oh, tax-paying citizens of Los Angeles, how many of you are that? And we are thanking you because Griffith Observatory is owned and operated by the city of Los Angeles. A lot of people don't realize that we are your city observatory. How many cities have that? Not many. So we love to say thank you, and we are owned and operated by the Department of Recreation and Parks. So we're a city park, but it's just a really cool, special city park. That's why, coming to the observatory is free, so free entry and all that. So we hope that you will consider becoming members, Friends of the Observatory, and we thank you for your support through your city taxes. Okay, at this point in time, we usually like to say 2 last things by way of introduction. One is you can keep your cell phones on, but we recommend that you do not, because there is no signal in here. This wonderful mesh cage around us keeps any signal from getting in here. So your phone will be roaming, looking for signal, and then it will run out of battery, and then when you're trying to call your ride share and you can't get home, and then your children forget you, all of these things, it leads to very bad things. So we do recommend that you turn your phone off just to save battery. It won't ring, so you won't disturb us. And then lastly, Bill, would you like to tell us about the music that we were listening to?
Walk of shame.
Walk of shame.
The exit.
Oh, Bill's doing the walk of shame. Why don't you go? I'll come back to walk of shame in a sec. Thanks. Go ahead.
So you all, those of you who have not been here before, we play a little game because astrophysics is already really fun, but we like to make it even a little more fun. And I say that without any irony. So what we do is we have this game that we have not figured out a name for. Maybe one of you could name it for us someday. But you heard music clips playing as you came in, and each one of those songs or pieces of music is going to be, you'll see, is associated with a story that we're going to present tonight, either by title or lyric or theme or something. So if you get that connection, you remember the piece of music, you can shout it out when that story comes up during the course of the show, and you win a prize if you're the first one and you're correct. And anything that identifies the song, you know, that Rolling Stones song or whatever is fine. And the prizes are down here. And there's all kinds of fun prizes. I'm going to go through these quickly. We have beautiful shots of the Eagle Nebula. We have these, which are, I won't hold it up, but it's basically a paper model of the New Horizons spacecraft that you punch all the pieces out and it gives you instructions on how to put it together. It's really cool. We have a little info sheet on Europa, which is a very interesting, beautiful place. And we have calendars. Now, this is sock drawer. You could just do the talk one. So these are beautiful, wonderfully produced calendars. Some of them are specific to Griffith Observatory. Some are Mars exploration rovers, things like that. Besides being beautiful, the other thing they have in common is that they are all absolutely out of date. But calendars can be reused again, and here at Griffith Observatory, we absolutely invest ourselves in reduce, reuse, and recycle. So I want to point out that this lovely, for instance, 2015 Griffith Observatory calendar, and even in this age of Google, it's fine to have an actual paper calendar. 2015 calendar will be good again in just 2026, just 7 years from now. And I know some holidays and things will be screwed up, but the dates relationships will be correct. 2016, you've got to be a young person for this because it's not good again until 2044. 2017 is good in 2028. So this, for instance, is 2017, 2018 is actually going to be good in 2023 and then 2029. You can X that out and write it in. So you throw them in your sock drawer, you forget about them, but you put a little reminder, a few days before New Year's of that year, pops up on your phone, and you go, oh yeah, I got a calendar. So that's it. Those are the. Oh, I'm sorry. Yes, Jeff has a beautiful. Now this is a very meaningful gift because this is the James Webb Space Telescope. And our speaker tonight is going to tell you all about this incredible mission. So if you want to be part of the James Webb Club, come on, guess a song right and then come down here and get your... we have plenty of these posters if you'd like. And we even have rubber bands to take them home with. That's it. Have a wonderful show.
Now, for those of you who have not been here before and have been wondering this entire time, what are they talking about walk of shame? The idea is that if you need to leave, you need to go out the back. Don't go out that way because you will have to do the walk of shame. That goes to a closet, and then you would have to come back out and walk past everybody looking sheepish and feeling embarrassed because you missed this announcement and went back there anyway. That side takes you to a labyrinth that descends straight into hell, and so you don't want to go down there. But if there were to be an emergency, we would lead you through the labyrinth and get you safely. So that is an emergency exit, but you don't want to try that, because it's dangerous. You never knew it was so exciting coming to a free program at Griffith Observatory. And then the last thing I want to say is hello, live stream people and YouTube live video people. We're glad to have you here too. Everybody's laughing at me. Maybe it's because okay. So I don't know why. I hope I'm not the first story. Okay, so I think we got it all covered, right? We got it all covered? All right. So, first Friday of every month, and today is Friday, September 6th. You could look that up on a calendar, probably from some time long ago. You guys probably all know why our first topic tonight is moon landing is hard. How many of you watched today or tuned in or followed on Twitter or whatever?
Why? What happened?
Well, we'll tell you all about it.
You will hear all about it. And then our guest comes, and we're going to hear all about Countdown to the Webb Telescope. We can't wait to hear it. Everybody is waiting with bated breath for this telescope to come together, to go into space, and to start making wonderful discoveries. And we're going to hear all about it from our guest from NASA headquarters, Dr. Eric Smith. Thank goodness for Burning Man. And let's say thank goodness David got back from Burning Man. And then we have some amazing headlines. Followed by the Sky Report, delivered not by Tony, but by Patrick. Pretty pictures and break gives us a little bit of a moment to shuffle around, go outside for a little bit if you need to. And then the second half, we have a bunch of headlines. I probably won't go through them all. Stormy and fiery and hot weather. Mars did not pass gas. Who wrote that one? Is that you? Yeah, okay. You have Jared to thank for that one. Hungry, hungry, sad Jay. Oh no, we cut that for time. Okay, well, we can tell you about it anyway if you like it. Take that, Drake equation. Anyway, there are a lot of stories in the second half that will come back after break. So let's, without ado. Okay. Turn to today's story, which is not a funny story. Oh my goodness.
Yes.
A total winner. Yeah. That was the Indian national anthem, was one of the walk-in songs. That was you? Or you? You? Oh, marvelous. And how beautiful is that national anthem? It's so beautiful and so contemplative and lovely. So that is, regardless of the outcome, that was already long planned to be in our program. There was the mission Chandrayaan-2 was launched to the moon in July of this year, and was attempting today to be the fourth nation on Earth to land on the moon. Not a human, not a manned landing, but a robot. So the United States has done it, the former Soviet Union and now Russia has done it, China has done it, and India was endeavoring to do that today. So since July, it's gone on this crazy little sequence of getting higher and higher in its orbit. And we just like this because it's kind of fun to see how it captures the moon right, there. And now it goes circling around the moon and brings us up to today. Today, the lander separated from the mothership and started its descent to the moon. This is a picture taken from Chandrayaan a couple of weeks ago, and there's a kind of a nobody took that picture. This is a superposition of the spacecraft with the moon in the background. These were the proposed landing sites, and if you were following along today, the separation of the lander from the orbiter was nominal, perfect. Everything was beautiful. It was going down, 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 and with about 1 minute to go, there stopped being any information on the feed. If you watched these before and you know that it was supposed to land at 1:25 and 1:24 is there and everyone's holding their breaths and it's very exciting, and then 1:25 comes and you're just waiting for that signal. They say we've got signal, it's down, and then it becomes 1:26 and then it becomes 1:27. It's the anxiety of that and the sadness of that is really, really hard, and that is what happened today. So all of those very excited engineers with the Indian Space Research Organization waiting, and unfortunately there was no signal from the craft. So what was the cause of no signal? To be determined. I will say that it was observed by radio astronomers in the Netherlands who showed, this is just showing using like police car does, a Doppler radio wave to just measure its speed, how fast it's going, and you can see it slowing down. But just before it lost signal, you can see these little wiggles in the Doppler shift. These are not interpreted, these were just posted by the scientists who took them, but that is not what it's supposed to look like. So that is very sad. Actually, at 7:30 tonight, there was a press conference, so we started our show, and I believe that We have some people monitoring it to see if there's anything new or that we are not already aware of. As I mentioned earlier, it was heartbreaking to watch. And finally, after maybe 10 or 15 minutes of waiting, they basically said subsequently communication from the lander was lost. Data are now being analyzed. So that's where we left that mission today. It's an amazing accomplishment. There's still an orbiter that's going to be taking data for months. The lander only had 2 weeks of energy. But nonetheless, we know they wanted to land. We all wanted to see them land, and so that's a very unfortunate circumstance today. Moving on, I just want to give a little bit of background before introducing our speaker. As you know, we're here because we want to study space and all the things that are in space. That's what astronomers do. This is what we tell our 5th graders in the field trip program. Astronomers study space and all the stuff out there, and we do that using a lot of telescopes. So no, that's not a picture, and they're not usually that close, but NASA has launched a lot of missions, telescopes and spacecraft going to different planets and destinations in our solar system. One of the ways to look at all of these various programs is in terms of their size, and this might be a little bit new to you. So we've got them here, flagship class, which actually has been changed, I saw recently, to large strategic science class, but I've asked our speaker today, is that what they're calling? He said, they still call them flagship. But I said, that's good, because I went back to flagship on my PowerPoint. New Frontiers class, we'll come back to this, Discovery class and Explorer class. And those are from largest, most expensive, down to smallest, least expensive, and also the ones on the right, the less expensive ones, are what we call PI driven, like the way New Horizons was driven by Alan Stern as the principal investigator. It's a scientist, usually at a university or a research lab. It's not a like Hubble that was built by NASA and operated by NASA or a consortium for NASA. So these give you the various scales, and to give you an idea, Hubble and Voyager, Cassini, these are all major missions that are big destinations, big science, big bucks. As we used to like say, no bucks, no Buck Rogers. Down to the smaller missions that have more specific purposes, like TESS that David will be talking about later, very specifically designed to do one thing, but do it right and do it well and do it within a limited cost portfolio. Even smaller still, you can get to CubeSats. That's becoming quite the cottage industry, and you've heard about some of those before. But I wanted to just give a little bit of a nod, because this dates back to my era when I worked with NASA and for NASA, the great observatories. Compton, these are in order of energy: Compton, Chandra, Hubble, and Spitzer. Gamma rays, X-rays, optical, and Spitzer is for infrared. And they are big. They're called the Great Observatories. So that's what I call space observatories. So not only are they all major missions, but they cover the wavelength regime from very high energy gamma rays to much, much lower energy infrared rays. But they also let us do these multi-wavelength images where you look at the same thing, like this supernova remnant, see what it looks like in X-rays, see what it looks like in visible light, see what it looks like in infrared or heat light. And together you can stitch together a lot more about what's going on, what the physics of that thing is, than if you're just looking at it in one color or one wavelength. Here's another example of a galaxy. You can learn so much about it by looking at the different... Oh, is that me or is that him?
Go ahead.
Sorry. Okay. And then here's our Milky Way galaxy. Kind of unbelievable in all different wavelengths. If you were to look at the Milky Way crossing the sky, but you had X-ray eyes or infrared eyes or gamma ray eyes, then you would see it looking something more like this. So these are the great observatories, and tonight's talk is really the start of kind of a great observatory fest. As you can see, the Compton Gamma Ray Observatory has been retired, but all three of the other three are still operational, still giving us great science. Spitzer will retire in January. And Chandra, which is in X-rays, I don't know, X-rays is, oh, okay, it is his, is celebrating its 20th year. So in fact, over the next couple of months at All Space Considered, we will be focusing on those. In November, we have a guy, actually my old lab partner from grad school, Pat Slane, who works on Chandra, is going to be here. And in January, and especially for those of you who are regulars and come back, the January 1st Friday All Space is on January 3rd. And that makes flying home ridiculously expensive if you're going to go visit family over New Year's. So we have been discussing are almost certainly going to postpone the January All Space Considered because it's really hard to get back on January 2nd and then do a show on January 3rd. But that works out well because Spitzer is going to be retiring and they are going to join with us here, and we're going to have a little celebration event that will be all Spitzer considered. He came up with that. Good one. Okay. So, coming back to the two at hand in optical and infrared, these are Hubble and Spitzer. But there is a new kid on the block that is going to be adding to our science knowledge and covering that same wavelength range, and that is the James Webb Space Telescope. If you've been following the news, you know that they hit a big milestone in the last couple of weeks. They have all of the parts are now assembled together. The whole kit and caboodle is all assembled together into one big spacecraft, getting ready to go through final testing and to go be launched. So we are overjoyed tonight to have as our guest Dr. Eric Smith, who is from NASA headquarters. And so Eric, why don't you please come and join us? Patrick. Yeah. So let me tell you two quick stories about Eric. One is we've known each other for years because I was on Hubble, he was on Hubble. We're Hubble cousins, Hubble siblings together. And then the other thing is he was supposed to come here last January and do this talk, but we had that pesky little government shutdown. So some of you might remember that we had to say, well, Eric Smith had to, they didn't let him travel. So just a mere 9 months later, we are so glad to finally welcome you here. And so, Eric, why don't you tell us a little bit about Webb, and then we'll have a chance to ask questions and discuss.
Okay, well, thanks, Laura. And I guess the delay worked out well because now we have some really exciting news to talk about here. One of the first things that I like to talk about when I talk about the James Webb Space Telescope is say, well, who the heck is James Webb? So this is the James Webb that we're talking about here, not the ex-senator from Virginia, but the man who was really the architect of the Apollo program, NASA's second administrator. But the reason it's important for us here as scientists is that he is the person that insisted science be done within NASA. Many of you may remember that the Apollo program was really showing American superiority to the Soviet Union. We're going to beat them to the moon. We have the best rockets, all that. That's really all that Kennedy cared about. But Webb, who was a bureaucrat by training, knew how to work the levers of government, knew that he had to have the best scientists and engineers to complete what the president wanted. And to get those people, he had to let them do their science and engineering research. So the only reason we have science at NASA is because of James Webb, who was a lawyer by training, actually. So why are we building the Webb Space Telescope? Well, we're building it because of something that Hubble couldn't do. After Hubble was repaired in 1993, the director of the Space Telescope Science Institute, Bob Williams at the time, said he was going to do an experiment and point the Hubble at a blank piece of sky. I think there were maybe 4 stars in the field of view, otherwise completely blank, to see what could you see if you really expose for a long time in the sky there. And of course that picture now is famous as the Hubble Deep Field then. There was other instantiations of it, the Hubble Ultra Deep Field.
The Hubble Super Duper.
The Super Duper, Supercalifragilistic Deep Field. What they were looking for in these deep fields were signatures of the first stars and galaxies. Can we see the universe turn the lights on, in other words? And what they found was no matter which one of these objects they looked at, it was not one of the first galaxies. And so as capable and as amazing as Hubble is, there are some places where it has fallen short. So that actually told us, now this is in the mid-90s, that what we needed to do if we wanted to see some of these very first galaxies was to build a larger telescope and one that was optimized for the infrared. And I'll do a brief little physics discussion about why that's the case. So galaxies emit a lot of their energy as starlight, which we can see in the optical. And so here you see the black body spectrum, the amount of energy that comes out as a function of wavelength, peaking at around the optical part of the spectrum for a redshift of 0 object. So redshift 0 means it's local in our own universe. Now, as you're looking out in space, you begin to look back in time. Astronomers measure that in terms of redshift. And if you march out in time, farther back in space, the wavelengths of the light get stretched by the expanding fabric of space-time. Think of if you were shaking a rope with a friend of yours and you started backing up with it, you would be flattening out, increasing the wavelength. The same thing is happening as light travels across space-time to us. It's getting shifted to the red. And so if you move to a redshift of 3, you can see where that peak used to be in the optical. It's now in the infrared part of the spectrum. And if you go out to a redshift of 10, which is about where Hubble can see to, maybe a little farther than that now, you're starting to get into the mid-infrared. So to find these early galaxies, you would like to optimize to be an infrared telescope. That's where the light is. The other thing that redshift does is it decreases the surface brightness. It makes the objects harder to see. They've become fainter. So you need an infrared optimized, bigger telescope. And that's really the genesis for the James Webb Space Telescope. It was this phenomenon that Hubble looked for, couldn't quite make it, and it told astronomers, the astronomical community, what the next step needed to be. Now, one of the benefits you get of having an infrared telescope that you've built for this is that it's also going to be very capable of looking at objects at cooler temperatures. Again, if you look at starlight, stars emitting a lot of their radiation in this visible part of the spectrum, that's a characteristic temperature, several thousand degrees Kelvin. If you have an infrared optimized telescope, it's going to be more sensitive to cooler objects, and so you'll see the universe in a slightly different way. You'll be looking at different physics, and we'll be most sensitive to objects in the hundreds of Kelvin range locally. This is more for experiments that we would do within our own galaxy. So these are the basics of the physics behind Webb. Now, what were some of the things that astronomers were thinking about when they said, hey, let's build this large infrared optimized telescope? Well, you might imagine they had plenty of things they wanted to do. So initially, it was this emphasis on finding the first stars and galaxies. But since you can see those first objects, you can now watch them evolve throughout cosmic time. So you can do a lot of experiments, as it were, about the structure and how it builds up in the universe. You can begin to penetrate, because infrared radiation penetrates gas and dust clouds more effectively than optical light. So you can watch stars forming in dust clouds within our own galaxy. The second to last question up there was something that we didn't think about when we were first conceiving Webb, because in the early 90s, does anybody know what the exoplanet count was in the early 90s? Well, it was when we were started at Webb, there was 2. We knew about 2 around a pulsar. There was no way you could observe them with Webb. But it really wasn't part of the initial thinking. Now, when we talk about the instruments, you'll see that we actually will be super capable, but it wasn't really by design. It was only because of the incredible power of some of the instruments. So just for comparison here, people may be more familiar with Hubble. This is just a little statistics comparison between the two. So Hubble's mirror is about 2.5 meters in diameter. Webb is 6.5 meters in diameter, so more collecting area. Hubble is pretty beefy as far as telescopes go. It got to ride up on the shuttle, so they didn't really have to worry about mass, saving mass that much. We had to worry about that a lot. We were just a bigger observatory, so even though we are a larger collecting area, we're about half the mass of Hubble. Our wavelength coverage is from the reddest parts of where your eye can see out to the mid-infrared, whereas Hubble can see a little bit into the infrared out to the ultraviolet, so different wavelengths optimization. Hubble's a room temperature telescope because it's in low Earth orbit. Because we're infrared optimized, we want to be cold because you don't want to see the signal coming from your telescope, so our telescope is very cold. And also, unlike Hubble, we will be far away. Hubble was accessible by the shuttle, got repaired. We're going to go 1 million miles away, 1.5 million kilometers away, and we'll talk more about that later. Let's see. Last point there, Hubble went up on the shuttle, and because we're a partnership with the European Space Agency, they are giving us a ride on their Ariane 5 rocket. So a little bit about the telescope here while this little animation runs. We talk about 3 big components of it. The telescope itself, the gold hexagonal structure everybody thinks of. The spacecraft element, which includes that sun shield and also houses the propellant and avionics and batteries and things like that. And then behind it, those white structures you see there are the science instruments, and we have 4 of them. In the order they're listed there, the mid-infrared instrument is the one that sees the longest wavelengths for us. It was built by a collaboration of European countries, and it has contributions from the Jet Propulsion Laboratory. They did the detectors and the cooling for it. The near-infrared spectrograph was given to us by the European Space Agency. The big U.S. instrument is the near-infrared camera that was built by Dr. Marcia Ricci at the University of Arizona, working with Lockheed Martin in Palo Alto. And then the last bit there, the fine guidance sensor and near-infrared imager and slitless spectrograph, is the Canadian Space Agency contribution. And so they have a functional part, the fine guidance sensor, which keeps us locked on targets. I like to say Canada is helping their unruly neighbor to the south stay focused in there. And then the near-infrared imager and slitless spectrograph is their science instrument. So we knew we needed cameras and spectrographs. We needed a big telescope that looks a little bit different. We could talk more about that later. But to realize those things, we had to make a bunch of inventions. We had to invent technologies that actually enabled it. I won't go through all of them here, but some of the most amazing ones I do have pictures of later on are the backplane, the superstructure behind the mirrors themselves, which are beryllium. We made them out of beryllium, mined in Utah, throw away 95% of the mass. So really all you have is 1 millimeter or 2 of beryllium sheet, whose only job is to carry 1,000 atoms thick of gold to do the infrared reflectivity. So all that structure is there to carry 1,000 atoms of gold to reflect the infrared light. So speaking of the science instruments, it's just these were the things in white in that animation. In the upper left corner is the near-infrared camera. This will be the workhorse camera that you'll see a lot of pictures from. It's actually a redundant instrument. It's got a top and a bottom half. They're identical. And that's because this is also the instrument we will use to make all those mirrors work like one. And so it's completely redundant. Should one camera fail, we could use the other one, and that way keep all the other instruments able to work, and you wouldn't lose their functionality. The upper right is the near-infrared spectrograph. That's the European Space Agency instrument. For scale, because there isn't a person in the picture there, that's about the size of a baby grand piano, that optical bench there. It has a micro shutter device inside it that was built at the Goddard Space Flight Center, and that's about 100,000 or so little shutters that are about the width of a human hair that you can open and close, so you can isolate particular objects on the sky and let their light into your spectrograph. It's the first time we'll fly something like that in space.
Wow.
Bottom.
That's incredible.
It is an amazing instrument, and I think it's the one that astronomers will, it'll really be a workhorse, but I know it's going to be one of those things, it's going to be more complicated than everyone thinks when they first start, like, oh yeah, I can do that, and then they start working on it. Oh well, it's going to take a little longer. The mid-infrared instrument, bottom left, it's both a camera and a spectrograph there. It's being assembled actually at the University of Edinburgh, was where they had been putting some of that together. And then the bottom right is right before it was shipped. That's the Canadian Fine Guidance Near-Infrared Imager Slitless Spectrograph. So all four of those instruments got put, now looking at the left-hand side here, into this cage. We called it an integrated science instrument module, and that was lowered into the telescope structure. And on that picture you can see the goal of the telescope. It's pointing down at the floor. This is out at Goddard Space Flight Center in Greenbelt, Maryland. And then the picture on the right is just the very end of that process where they've lowered it into the ISOM compartment. Then once that was all together, we needed to test the telescope and the instruments together. So first a little bit about how that telescope works. We're called a three-mirror anastigmat design. So we have three main mirrors, elliptical, a hyperbolic, and another elliptical tertiary mirror. But there's also a flat steering mirror at the end that we can use so we don't have to slew the telescope for small motions. We can just move that mirror a little bit. The mirrors, as I may have mentioned, were made of beryllium. Each mirror segment can be controlled in piston, tip, and tilt, and we can also adjust its radius of curvature. So even though they look flat to the eye, there is some optical power in them, and you can sort of push the center in and out. We know that when we launch this, it will be out of focus. Just giving you that warning right now. But we can adjust it. In fact, because it's this infrared telescope that has to work at extremely cold temperatures, the mirrors now, they're out of focus because they're at room temperature, and it only comes into focus when it's extremely cold. It's part of the reason why it takes us so long from when we launch to when we get data back. We have to cool down so that the mirrors are smooth as they were supposed to be at cold and not bumpy as they are at room temperature. So did we test that? Well, of course we tested that. We took it down to the Johnson Space Center where we refurbished the old thermal vacuum chamber that the Apollo mission used to test the Apollo spacecraft. They used it to heat the spacecraft so they could test the effects of moving the spacecraft and how that might affect the astronauts. And of course we wanted to be just the opposite. We made it a cryo chamber so that we could drive things very cold. It's interesting when you go down there to work, on the side of the chamber it's a National Historic Register facility. So I thought that was kind of cool that we're doing modern day technology in this historic structure, and they didn't make us wear skinny black ties and get fruit nuts. So that was good. We didn't have to go to all that trouble. But this was after we did the test, and sure enough, they were able to move all those mirrors and exercise all the instruments, and I'm delighted to say that it will meet the scientific promise it has once we get it on orbit. Everything worked as planned, so that was very exciting. The structure that lies behind that telescope, even though we're just carrying those 1,000 atoms of gold up there, 1,000 atoms thick of gold, it's this backplane, this structure made of a carbon composite material. It comes in thin sheets that they lay up and epoxy together. It's incredibly strong, it's very light, and it has the property of a lot of things on Webb. Its behavior as it changes temperature is very well calibrated. And you can see the little note up there about how precise it has to be. We have to know how this is going to change to a fraction of a human hair, because that will affect the image we get back on the telescope. In fact, we were able to see when we were testing it down at the Johnson Space Center, there was a camera at the top of that chamber. They would shine down, and that chamber wasn't as cold in the top as the rest of the chamber. And just that very slight exposure to a few degrees temperature caused some of the insulating material to feel a change in temperature. And that incredibly tiny stress could be seen through the backplane. So it carries that information to the optics, and we have to be able to correct that out, and they were able to. So the other characteristic thing, other than those gold hexagons, is the big sun shield for Webb. It's our parasol that we use to block infrared light. Most telescopes block the stray light with a tube. We are a naked telescope. We don't have a tube. That's because we have most of the sources of infrared light to one side of us. We'll see that in an animation later. But by keeping the sun, the earth, and the moon more or less on one side, we only need to protect ourselves on that one side from this, the infrared radiation. Being a fair-skinned person, I love that last little thing there, SPF of 1,000,000. I could use that. Now, the spacecraft element, which is both the sun shield, here we see it all folded up in its launch configuration, and then the spacecraft bus, which is essentially it's the infrastructure that enables the whole observatory to work. It's where we have our reaction wheels, our gyroscopes, our fuel tanks, the batteries, the electronics. They had completed their environmental testing, so we subjected them to the vibration of a launch of an Ariane 5, the sound from an Ariane 5, and the thermal stresses they will feel, which are different than the telescope. This part only sees more or less room temperature. It sees the sun all the time. The telescope never sees it. And it's in fact that great contrast in temperature that means we can never test the whole thing in a thermal vacuum chamber on Earth. There's no chamber big enough that would let you get the heat on one side and the cold on the other side and not be an infinitely large chamber. That's what we have space for. So, 2 weeks ago today, as Laura mentioned, it all came together finally. And if you were to take a trip just a couple miles south of LAX Airport at the Northrop Grumman Redondo Beach facility, if you know anybody who works there, make sure you get them to go to the observation room. Anybody can get in there. If they work at Northrop, their badge will let them into the observation deck, and you can go see it yourself down there.
Anyone from Northrop in the audience? You need... Oh, great. Well,
Yeah.
you've got 100 new friends.
But I did exactly what you said. I saw day before yesterday. It was a thrill, a treat.
It's wonderful. Well, okay, everybody, there you go. Now, before we talk a little bit about some of the science that we suspect they're going to do, I'll take time out for this is a paid commercial break here about the people who've made this all happen. So there's a lot of words up on the slide here, but this is an international endeavor. Large, great observatories, like Laura mentioned, are pretty much all built with international support these days. And so I think Spitzer may be the last such observatory that will ever be built just by one country. They're all future missions are all international partnerships. The lead for this was the Goddard Space Flight Center, but we had contributions from almost every other NASA center. ESA supplied us with an instrument and the ride, the Ariane 5, which is the world's most successful, reliable rocket of its class now. So that's very comforting to know. You have a nice, safe ride. Canada supplied that fine guidance sensor. Both ESA and Canada are supplying people to work at Space Telescope Science Institute. So there'll be scientists on staff there. And then the main industrial contractor was Northrop Grumman, and they worked with Ball Aerospace and many other companies to make this come together. And of course, like Hubble, this will be the science program will be run by the Space Telescope Science Institute, but they will also fly the bird, as they say, this one. So it will actually be operated from Baltimore, where STSCI is. Hubble was run out of Goddard. So speaking of where things were built, this is just a chart we show of all the companies across the US that had some say or they contributed to Webb. And we like to take this around with us if we're traveling to any place in the country to try to mention if there's anybody nearby. Of course, here in Los Angeles, you have Northrop Grumman nearby, but there are other companies in the area. One last bit on the commercial. Some people like to talk about NASA spin-offs. I view that they're valuable. They're a side benefit. You don't do these things to get spin-offs. There would be cheaper ways to get them. But it is nice to know that these incredible mirrors we had to make and invent have allowed another company to use the metrology technology to make something that eye doctors can use now for improved LASIK measurements. We're using a lot of the other metrology techniques for higher tech business. In what I consider an amazing piece of future heritage, the application-specific circuits we had to invent were invented early enough in the program that they actually got to use one on the last servicing mission for Hubble. So we invented something and sort of gave it to our predecessor. That was pretty interesting. And then the detectors we had to build have become the foundation for missions after us and will be for future missions as well. So we're all together. We're down at Northrop. We have about 1 year of testing to go. They'll practice a deployment. We'll see that in a second. Then they'll fold everything back up, and then they'll take the whole observatory in that configuration you saw before, where it was folded up, and they'll, again, shake it like it's going to go on an Ariane. They'll blast it with the sound of an Ariane, and then they'll unfold it all again and fold it back up. So in about a year, it'll be ready for its launch, and that means we'll take a boat ride. We are going to take a ship from Los Angeles through the Panama Canal down to French Guiana, where it will be launched by the European Space Agency. It sounds counterintuitive, but that's actually how Arianespace, the primary contractor, get their large parts down there too. They barge them in, I like to say. That's an easier route. They're very close to the coast. And the rest of the country's infrastructure isn't as good for things like large bridges, taking a lot of stress. So we will take a ride, a boat ride down there.
Take it to ride.
Sure.
Now, I mentioned that we're going to be 1.5 million kilometers away. Anytime you have two bodies that orbit one another, a two-body system will have 5 places that are stable or semi-stable in the gravity field of this rotating system. This was discovered by a French mathematician in the 19th century, Lagrange, and where we are going is that L2 point. And so it sits outside the Earth and the Sun. And if we run this little animation, what we actually do, you see the moon whipping around the Earth there, and you'll see Webb come in, and we actually orbit about that second Lagrange point. So we keep the sun shield, keeps the sun, the Earth, and the moon on one side of us. We're not in the shadow of the moon because we got to be able to communicate back to the Earth. But the size of the sun shield means that we can keep those things on the hot side and keep the cold side on the cold side. So now the part that gives everyone, causes their heart to skip a beat. This is how we get out there. Oops. I wanted to hit the volume button. So it's an animation that folks at Northrop Grumman put together showing the sequence of events. Once we get released by the upper stage from the Ariane, we go through a series of maneuvers and deployments. You can see on the top the time after launch, the distance will come up with the activity, and you can see a little graph showing where we are in our journey. See, the solar array comes out very quickly, so we have power. We start to do any course corrections we need to make sure we're going to the right orbit out there at L2. The smaller the correction we have to make, the longer our life is because it saves fuel. Right about the time we get close to the moon, our high gain antenna comes out so we can communicate at a high data rate. You can see about 2 days we're past the moon. Now we begin the major deployments where what's called a pallet that holds the sun shield, the forward part folds down. We'll follow that by folding the back part down. I got to watch them test this at Northrop Grumman. They do a gravity offload to test the system. Now, once those are down, we want to move the telescope away from the spacecraft because it is a little warm itself. So we telescope up on a tower about 5 feet. Now, the covers that protected the sun shield during launch are released and they roll back. Some covers in near the spacecraft core do the same thing. And once those are released, we can actually begin to push out concentric tube telescope booms to extend the sun shield. There are 5 layers to this sun shield, and it's critical that there be separation in these layers so that heat from one layer can escape out before it hits the next. So they'll tension up the system, which is just a pulley system that raises the layers apart and provides tension to them. The next deployment is a flap in the back that you can think of as a sail because it's there to balance the solar photon pressure that would tip the telescope over if that were not there to balance. The center of pressure and the center of mass aren't exactly the same.
That's ridiculously cool.
That's the cryocooler starting for that mid-infrared instrument, a little refrigerator to keep it super cold. And here, after about 10 days or so, the secondary mirror comes out, and it's at this point when light can actually, focused light can get into the science instruments. There are a lot of radiators that get deployed during this sequence. And then we bring drop leaf table style, the 2 wings come out. So after about 2 weeks, the major, let's call them visible deployments are done, but then the mirrors themselves are held down to that backplane structure for launch. They get released and we begin to start moving those as they're cooling down and begin to bring them into shape. It takes about a month for us to get out to L2. We're cooling down this whole time, starting to commission the instruments. We're a little bit like a planetary mission in that we'll launch, fire and smoke, a lot of activity. The first data don't come out until 6 months after that. So after the launch, if you don't hear anything for 6 months, It's okay. Well, we actually, that's a big activity we have now, is how do we bring along, the public, the taxpayer, with all the activities that are going on, even though we're not seeing data yet.
Well, those first 2 weeks, will we be able to follow along live with each and every deployment?
Yes, that's going to be a big part of, again, bringing people along for the ride. Is we have social media accounts describing, this is what's going to happen today, and here's how we know that happens. We don't have any pictures, and there's nothing that will be taking a picture of us while we're out there. But we'll have, great computer simulations showing the state of the spacecraft. So once we get out there, what in fact will Webb do? So we know already that it will be looking for these first galaxies. And here you see an enormous simulation of the universe with dark matter in the purple, where visible matter is accreting at the dark matter centers and galaxies are beginning to form. This is the reason we built Webb. We know this is the science it's going to be able to return for us. So that's certainly exciting. The other thing that has become, I think, maybe even more exciting for a lot of people is this notion of exoplanets. As I mentioned, when we first conceived Webb, we didn't think we were going to be doing exoplanets because we only knew of 2. Well, now we know of thousands. And the way Webb will really contribute is in the cases where you have a transiting exoplanet, an exoplanet that goes between us and the star, and we will look to see if that planet has an atmosphere that subtracts certain elements of starlight from it. So we are really going to be looking for habitable atmospheres with Webb. It's got the mirror size needed to do this. It will still be challenging for Webb, but it will be the first telescope that you'll really be able to go after this in a very big way. And so this is something that we already know is going to be a big focus for Webb, even though when we built it, it wasn't conceived that we would be doing that. The infrared capabilities of Webb will allow us to peer inside the birthplaces of stars and planets within our own galaxy. And we already have seen there are programs, I'll talk a bit about more of those in a second, where people are going to be doing just this. So another way to watch star birth in our own galaxy. Even though it's a big telescope designed to look at the distant universe, it will be able to do amazing things within our own solar system. Now, because of the configuration, we can't look at the inner solar system. So we can't look at Venus, we can't look at Mercury, can't look at the Earth. We can look at Mars. You can do weather, global weather on Mars by looking at it with Webb. I really think most of the time will be spent on looking at the large moons in the outer solar system and the trans-Neptunian or Kuiper belt objects. Again, with the infrared capabilities, it's a great thing to study those. A lot of words up here. The main thing is the link at the bottom. We already know some of the first things Webb is going to look at, and these are the so-called early release science programs. These were competitively selected, and they range from distant universe observations to looking at bodies within our own solar system here. So already the community knows what they want to do for the first things that Webb is going to look at. And if you want to follow along, like every person and or spacecraft these days, it has a Facebook page and a Twitter account. And
Is it going to talk in the first person like, oh, I stretched my wings today?
Actually, a bunch of us don't want it to do that.
I know, exactly. I was like, oh, please.
Yeah. So, yeah.
It sure is cold out here.
Yeah. I can already see the bad jokes. They won't be from me, I'll tell you that. The top link there is the main one, and NASA has a lot of, you can get to a lot of hardware images and movies and whatnot, and the one below it, the webtelescope.org, is the one that the Space Telescope Science Institute runs, and that's going to be focused more on the science that comes out. So that's a little bit, it doesn't have as much on it right now because we haven't done any observations yet. But I'm looking forward to the launch in March of 2021. 6 months after that, the amazing science will start coming out. And so, keep on the lookout for those, and I would be happy to take any questions you have about Webb now.
So we have a little time, 1, 2, 3, and then I'm going to look to that half of the room, which doesn't have any hands up. So get your hands up in a second. We're going to take these 3.
Does Webb have a gyroscope to stabilize it? And is there going to be a possibility of, if everything doesn't work right, to have a servicing? 1.5 million miles is a long way, but a manned servicing mission?
Okay, so I'll repeat the question back. Does it have gyroscopes? How does it stabilize? And the one that a lot of folks ask, is Webb serviceable? So it does have gyroscopes and reaction wheels. We use the reaction wheels to point the telescope by using the conservation of angular momentum. We have 6 wheels. You'd need 3 of them at a time. They're all at slightly different angles, and by spinning them at different rates and changing that spin rate, you can move your telescope. So that's how we'll move about the sky. And then eventually those wheels can become what's called saturated. They spin up too fast, and you need to de-spin them, and you do that by pushing against rocket thrust. So we have thrusters that we would push against the reaction wheel, and that gives us our life-limiting feature, which is fuel to desaturate the wheels. We're going to carry up enough fuel for about 10 years of operations. If we get a good injection, meaning we don't have to burn any to correct our orbit, we'll get more. And I suspect as people at the Institute learn how to construct an observing program that builds up this momentum in a very small way, we may even get more time. Second question about servicing. Because we're going 1.5 million miles away, we have no way of sending people there today or even in the Webb lifetime. So serviceability was not something we built in to the design. In fact, our instruments are distributed in the sense that you can't just go in and take that NIRCam out because the electronics are in a different place. What we have done is placed optical targets on the bottom of the spacecraft in the ring that attaches to the rocket. And so in the future, if there's some advanced robotic thing that could go up there and latch onto that, it could possibly refuel. That's about the only thing you could do for Webb. If there's a flaw, it's so distributed you couldn't repair. One of the reasons Webb is so expensive is that we've had to have a very elaborate, detailed, lengthy test program to make sure we have redundancy and multiple ways to do things so there are no failures on orbit.
Yes.
The micro shutters.
Yes.
I assume those are for occultation.
Well,
It's keep the image focused on one thing. So you can,
right. We'll use those primarily when we want to take spectra of lots of galaxies in a field, but we don't want spectra of stars that happen to be in the field or interesting or uninteresting nearby galaxies. So we'll keep those parts of the sky blocked out, and we'll just let light in from the things we want to see. Another place where we might use those is in, say, like a cluster of stars where there's a few hundred stars in that cluster. We only want the spectra from those and not the background stars. So we just let the light in from the objects we're interested in.
does that whole thing move in and out of the way, or is it always there?
You can move it into the field of view. That same instrument has a more traditional, just a long slit spectrograph, a single slit, and it has an integral field unit. So you could move your small objects into those fields. Otherwise, you just open or close the shutters you need.
Okay, and did you not have a question? You were the third? I thought someone over here was third.
Yeah.
Okay. First of all, thank you for a great talk. And I have a why don't you?
Okay.
Why don't you offer a ride to some university to build a CubeSat for the purpose of observing the telescope as it deploys and does all that stuff?
So one of the things I did over the past year was look at that very possibility, and it's actually dangerous. So the way, if you wanted to observe the telescope, the way to do it would have been to build cameras right into the thing itself. Most spacecraft don't do that. So now, after the fact, we looked at, could you take things on the Ariane 5 with you to go? First off, Ariane would say no, we're spec'd out for this. And you then have you'd have to worry about control of your CubeSat, a few $100,000, $10 billion observatory. Don't want any of that. So in the end, we even looked at, well, what about a large telescope? What if you built, say, for the lunar program, another Hubble, and you sent that a day or so later, and then afterwards, it went back to the moon, it did something there. Then you ran into the problem of the launch window constraints get so tight. If somebody has a problem, then you miss it, and now you can't catch it. So you'd have to get a CubeSat. The other thing would have to get pretty close, because the telescopes on a CubeSat are going to be only this big, and so to make it an interesting image, you'd have to get close enough that people worry about collisions.
Anyone on this side of the room? Yes.
Hi, I don't know much about telescopes or space technology, but do you know if machine learning was used for any major or minor design choices in Webb?
To my knowledge, machine learning was not used in any of the design aspects. Much of this design work was done in the early 2000s, before a lot of the machine learning was, I think, applied in many industries. I think what we're trying to do now is use it more in designing observing programs and mining data for Webb, and that's where I expect it will make a big difference there.
So I have a question, and then lastly, but I'll go before you, because what do you want to observe yourself? And are they giving you time just because of all the years you've put in? I guess that's part two.
So one of the things when you work for NASA, and particularly at NASA headquarters, you're there to create science programs for the science community. So we don't get any time at NASA, and I think that's actually good, because we can actually do things very objectively. If my goal was to observe object X, it might influence my decisions as to how to fund
To
things or
optimize that instrument
optimize it for
yeah.
that. So we do things for the best of the science community. If I were going to pick something to look at, I would probably, one of the galaxies in my thesis was NGC 1275, radio galaxy, active galaxy. I would probably look at that to see about how the star formation in the inner region relates to any of the activity at the center, or is it a remnant of the collision that spawned the system?
Thank you.
But I'd have to write a proposal if I
Yeah.
were to do that. Yeah.
And our last, okay, two questions. You, and then I'm done.
My question was, what were you most excited to learn about from Webb, which you just kind of answered.
Well, that would have been if I was doing my old science again. I think the most interesting thing that I know it's going to do is probably some of these exoplanets looking for habitability, the TRAPPIST system. But as I was saying a little earlier, usually the best or the most fascinating science that comes from these great observatories is something we don't even think about today. So somebody is going to think of some novel use that people will initially say, well, that's a stupid idea, it's not going to work, you can't do it. And eventually it will be an amazing discovery. So that's what I'm looking forward to.
Okay,
They'll do
and
that,
our last question is at the top. Oh, I saw you too late. Yeah, go ahead.
Is there anything special about L2? Is it any noteworthy? Is it going to be a subject of research for the telescope at all? Is it anything like going on with L2?
So L2 is a special place because it's a semi-stable point, so you don't need a lot of fuel to stay there.
Is it just a point, or is it a planetesimal body?
It's just a point in space. There's nothing there. Because it's semi-stable, if you put something there, any perturbations to it, a little pressure, hit by something, it will fall off L2. L4 and L5, those points are stable. And in fact, if you look there, collections of dust exist in those places. But we go to L2 because it's far away from infrared sources for us. It's semi-stable, so we don't need to use a lot of fuel to stay there. And in fact, a lot of science missions have already gone there, and future ones are going to go there. So, but it's a big place, so it won't get crowded.
Okay, I'm going to call an end to the questions, sadly, because I know everybody has a few more, but we have a few things we just want to share before we go to our break. So let's thank Dr. Smith. And we made this poster for the talk tonight before seeing you today, so one of our staff, Jeff here, updated it a little bit there. As we said we would. Okay. David, tell us what crazy things happened in the playa.
Yeah, everybody here knows that I head off to Burning Man every year, well, most years. This year was my 20th, and this is what it looked like when I arrived. I went out for 13 days this year, so it was their early build week. We built a dome. Well, my campmates did. I watched them do it in 100-degree plus heat, but they eventually got it done. That's what it looked like at the end of one of the days. They got the outer sheets on it. Dust storms came and went. Some neighbors had a submarine art car that we had to listen here. You can hear it go by playing some reggae for us.
Turn it up.
So, and the dome actually does rotate, believe it or not. All good telescopes domes have to rotate, which is cool. More finished state, it looks like that. Dust storm going by there near sunset. Lighthouse came and visited us. That's another art. And it was a working lighthouse. One night it kept shining on my tent, and I was annoyed. I went out and said, "Oh, it's the lighthouse. I love that." So, this is what it looked like towards our theme camp. Not only did we build art that had a 20-inch telescope, a 14-inch telescope, and I think a 12. We also had a theme camp, get a little closer to it there. There's a meteorite museum and a truck and a structure. We had lectures there 3 days. Well, actually 4 of the days we had lectures. I gave one on Friday. This was the Meteorite Museum, and on our play structure there, we named it after a campmate of ours that passed away, unfortunately, last year, but he was really into meteorites, and his family gave us a bunch of money. On Kids Night, we gave out 150 meteorites to kids throughout the week. We would tell them, we would tell them it's a shooting star that made it to Earth, which gets them excited about it. The 2 women in this shot actually are telescope operators on Mauna Kea, one at Gemini, the other at JCMT, campmates of ours. We had a lecture scheduled there, and Celestron donated a 6-inch, really nice go-to scope, and we had an H-alpha filter on it that gave us some pretty good images. This is through a cruddy cell phone. The image looked a lot better through the eye, of course. At night, we did observing of the night sky. This was a beautiful time exposure here to get some stars. Believe it or not, it's a little more like suburban sky there. Burners are obsessed with LEDs and lights and lasers and whatnot. But you can see the bikes parked there. We kept them away, and when you went in the dome, we just had some red light. And this was on Kids Night. You can see the people observing through the telescope. And again, just a cell phone stuck up to it, a view of the moon early in the week. Our camp wasn't just all about observation. We had some fun, too. We had a... Oh, let's rerun that because it's too good. So, Space Fans, Space Dance.
You cut it short.
Well, the crew did. So anyway, our DJ on the left there, Kurt, it was awesome, and some of us dressed up a little bit. The 2 folks in the picture facing away are our DJ's 80-year-old plus dad and his wife. His mom, that they renewed their marriage vows, and our dance was the reception. It was very sweet. There I am in my silly outfit. So, thank you. I did an exploration one day, went out and found the Celestial Sideshow, which looked like a circus with celestial themes. They had anyway, astronaut holding up a mermaid, I don't know. Exploring on the playa, I came across a full-size lem. Yeah, it seems to be a 1-to-1 size. There I am climbing it. It was very cool, although it was closed due to not being safe to climb inside of it. Went to the very corner of the event, and I came across this little weird aliens that were hanging out. And the structure itself didn't provide much shade, as you could see, but there were records that were melted around the poles, so kind of fun. My camp got a little bit of good press. Space.com called us out with projects like Black Rock Observatory, a mobile observatory that facilitated astronomy at events like Burning Man. We think about 10,000 people looked through our various telescopes and came to lectures throughout the week. You can see it from space. You can watch the event show up. That's about 2 miles across from one end of the city to the other, so lots and lots to explore. Over 70,000 people go. Campmate of mine managed to get a flight. You can go out to the airport that's there and beg to get on, and if you're nice and say, I'm from Black Rock Observatory, they say, sure, we'll give you a ride. Of course, people go out there to see the man burn. This was the structure this year. They launched lots of fireworks and gasoline explosions too, and the man catches on fire and burns some more. And if you want to see any of the other art out there and whatnot, because there's lots and lots to see, you gotta go. So until next time, stay dusty, but that's all I'm going to tell you about Burning Man once again. So thank you.
And then finally, we wanted to tell you some stories that made scientists astounded. So here was one: UFOs are coming out of black holes and altering galaxies forever. Who knew? It's all very new science. But then we started seeing so many that we thought, okay, we're not even going to try to talk about one. We'll talk about, just in general, the whole issue of clickbait. So I was kind of horrified by that, and who wouldn't be? So we decided to have our little clickbait Hall of Shame. And I think you all know that you can follow us on Twitter or follow us on Instagram or on Facebook. I don't know if people follow what they do on Facebook. I don't do that one. But so send us some of your favorites. We think we'd be very interested in that. But so the quick translation, here are these: the red planet is swallowed by the sun, and there's the UFOs ones. Oh, I can't even see what some of these are. Just for building a worm tube. I don't even know what all that's about. But so there's our translation for each of these. The Mars one is just, it's going behind the sun, so we can't communicate with the Mars missions. The UFO one stood for ultra-fast outflows. I kind of like CNN just learned about multi-messenger astronomy. Anyway, Gaia shows us cool stuff. Anyway, it's kind of good to be a good consumer of information when you see these things and maybe go find out what they really all mean, because unfortunately clickbait is a reality of our social media landscape, and so they'll say, you'll hear the craziest stuff.
I think I've had city training to not click on this stuff.
Oh, well, don't click on it with a city city computer. Yeah, no, or come to us, send it to us, and then we'll tell you what it all is really about. So you can share it with the class, and you know how to reach us. So our last little segment before break is Patrick. You want to tell us what's in the sky this month?
Yes, indeed. What's in store for us in our evening skies? Well, if you look right in the evening, you can see the bright planet Jupiter. And yesterday, the moon was right by it.
How many of you saw that?
That
Isn't
was
that pretty?
really pretty. Yeah. And right below it is the red star Antares. Now, the moon was there yesterday, but tonight it's, we can go to the next slide, it's between Jupiter and Saturn. And tomorrow it will be next to Saturn. So look for that, and that's what you can see in the evening sky right after the sun is set through a large, kind of fairly large amateur telescopes. These images from astrophotographers provide us great views of Jupiter and the open rings of Saturn, of which you can see through a telescope. Here on the lawn, we have telescopes out every night, and of course our telescope is open on the roof, so you want to take a peek, especially for Saturn, because that's quite a treat. The other thing that you can see, but you need fairly dark skies to see it, far away from bright city lights, is this band of light that stretches from overhead between these three stars, called the Summer Triangle, and all the way down to the horizon between Saturn and Jupiter. That's our Milky Way, our own galaxy. And the brightest portion of it is kind of near the horizon, and you can see that if you're camping or you are far away from bright city lights, so that's worth looking at. A quick look at our moon phases. We have a full moon occurring on the 14th, and a week before that, there's a star party this Saturday, so you might want to come up to see Saturn and Jupiter. during that time. And then last quarter after that, it's kind of easy to see the Milky Way because we have fairly dark skies in that respect. So what about the morning sky? Well, in the morning, if you're an early riser on September 20th, the moon at 5 a.m. will be right next to this bright orange star called Aldebaran in the constellation of Taurus. And you can see quite a few stars in the winter sky, like Orion with its 3 stars in a row for its belt, and the brightest star in the night sky, Sirius. So there's a treat if you're up in the early morning. Now, our season's about to change. So autumn begins officially on September 23rd at 12:50 a.m. Pacific Daylight Time. And that's where the sun is located on the equator of the sky and in the constellation of Virgo, although you can't see that during the day. Basically, the equator in the sky is the Earth's equator projected into the sky. Now, having said that, I have to kind of say that autumn technically begins in the northern hemisphere on September 23rd. And at the same time, spring begins in the southern hemisphere at the same time. So if you have vacation home over in the southern hemisphere and you want to escape autumn, you can go ahead and fly over there right now.
Who doesn't have a vacation?
In the southern hemisphere, right, my vacation home.
Also, the orientation of the Earth in space with respect to the sun is that sunlight shines perpendicular to the axis of the Earth, and so the Earth turns around and you get, on this day, kind of equal day and night all over the world.
So like equinox.
Equinox.
Yeah, cool. In just a moment, we're going to turn off the light, show a couple pretty pictures, but I'm going to do something unabashed self-promotion. And that is that, and I forgot to put a slide in, but I'm giving a talk at Mount Wilson on September 21st. Thanks, that makes me feel good. So not only do you get to come up and hear me talk, but after that, there's observing on the 100-inch. Not the 60-inch, the 100-inch. So think about coming up to Mount Wilson. My talk is a little different. It's called If We Can Go to the Moon. And certainly James Webb Space Telescope will be mentioned in there because it's about grand things that we do when we put our minds to it and what it takes to do that. So I hope you'll consider coming. And with that, I want to say goodbye to our live stream audience. We always tune out at this point because we turn off all the lights and you can't see anything. So, so have a lovely evening or whatever time of day it is for you. And why don't we go ahead and turn down the lights and look at some pretty pictures. Oh, that one has to, I guess that was never on.